With new EVs like the Ioniq 5 and Lucid Air entering the market with 800 and 900 volt architectures, many are asking, why does Tesla still use the seemingly out-of-date 400 volt architecture? Welcome to 5 Years Ahead, I'm Brandon Kruger. A big thanks to the channel's newest Patreon supporters, Keith, Frank, and Ray. Your support is much appreciated. On the Q1 earnings call, Tesla was asked why they aren't using an 800 volt architecture and what the advantages and disadvantages are. I'll play the full exchange, or you can skip ahead to my summary here.
On the 800 volt thing, so it's really a case by case thing for the smaller platform vehicles like 3 and Y. There's some wins and losses with 800 volts. Not everything is better, and so we look at that platform, and we're not like ignoring the reality that you could go to a higher voltage, but there's nothing really encouraging us to do so on that platform. It's really about mass and power, and as you look at bigger vehicles, there are some advantages on those bigger vehicles.
Yeah, I would just quantify that basically, like our estimate is that going from 400 to 800 volts might save $100.
Yep.
It's not really moving the needle.
And you're changing many things.
Yes, right. Exactly.
From the charging infrastructure all the way through the entire vehicle system.
Yes.
To get maybe $100.
Yes, exactly. So, in the US, you've got 110 volts household power or voltage, and then in most parts of the world, you have like sort of 220. But really, it doesn't make that much of a difference, and appliances work pretty much as well, in say Europe as they do in the US.
Yeah.
So there's some the advantages are small, and the cost is high. Like if you say like long term, like years from now, does it make sense to probably move to an 800 volt architecture? I said probably, but it really needs a very big vehicle volume to pay for all the costs of changing from 400 to 800 volts. And then you want to continue with the.
I was just going to say that 100 volts is also kind of like a spreadsheet exercise, right?
$100.
Sorry, $100 is roughly like a spreadsheet exercise. Like, that you have to get through the full program to the end to see that maybe it's been whittled away to 50 or less.
Yeah.
On bigger vehicles where you're talking about higher power on the charging side or higher power from the battery to the power electronics, or you need more torque, so the current requirements go up. There's a little bit more semiconductor and actual conductor savings of going to the higher voltage, and so we do consider that for Semi and Cybertruck. But for the 3Y platform, where we've got everything running and the benefit is questionably small.
Yeah, it's basically zero for robotaxi.
Yeah, for robotaxi, it doesn't make sense.
To summarize their remarks, 800 volts wouldn't offer enough benefit to Tesla's current vehicles over their current 400 volt capabilities to justify the switch. Tesla already has the supply chain up and running for their current hardware at large scale. Also, some if not all supercharger stations would need to be upgraded to support 800 volt vehicles. Tesla surely would like to utilize existing hardware as long as possible since it has already been paid for. It seems like they may consider switching the 3 and Y platform over to 800 volts once the hardware is being built at high volume for Cybertruck and Semi, but I can't see both those vehicles being fully ramped before 2026. They also indicated 800 volts would offer basically zero benefit for robotaxi. This raises the question, why are other automakers so quick to adopt 800 volt architecture? I have a couple theories. I think one of the primary motivators is likely charging speed. This graph shows how pack voltage impacts potential charging speed. From my research, 350 kilowatt CCS stations are limited to either 350, 375, or 500 amps, although 540 amps has recently been spotted from an EV Go station. Given this limitation, charging at 350 kilowatts isn't possible without at least a 700 volt pack, and 250 kilowatts isn't possible without at least a 500 volt pack. At Tesla's current voltage, CCS stations would only be able to provide about 130 to 205 kilowatts. At the other end of the scale, Lucid, with their 924 volt pack, is able to reach their 300 kilowatt peak charge rate even on 350 amp limited stations. The other reason I suspect automakers are jumping on the 800 volt bandwagon is that their suppliers have already done the engineering legwork. LG Magna, Bosch, and Borg Warner all offer 700 to 800 volt powertrains for automakers to pluck off the shelf and fit into their cars. With Tesla engineering their own motors, inverters, and other power electronics, the transition to higher voltage will require much more effort than it is required from other automakers. Luckily, Tesla hasn't needed to transition to a higher voltage because they are able to extract more performance per volt than anyone else. The Plaid Model S is faster down a quarter mile than the Lucid Air despite using half the voltage. As far as charging, V3 superchargers are able to output over 680 amps for short periods, which makes them about 50 kilowatts faster than the best 350 kilowatt CCS stations at that voltage. So what does this mean for the higher voltage pack I proposed in the last video? Well, moving to 800 volts would require significant redesign of vehicle components and supercharging infrastructure. The 580 volt pack I proposed may not pose the same challenges. For example, the MOSFETs used in the Model 3 inverter, which is now the only inverter used for the entire lineup, are rated for 650 volts. There are many other components that make up an inverter that must also be rated for that voltage though. As far as superchargers, I did find a clue in this permit for an installation in Hawaii. It mentions, quote, partitions and handholds not required due to 600 volt insulation for all conductors, end quote. Now, I'm not suggesting Tesla specifically chose 600 volt insulation to enable a 580 volt battery pack. 600 volt is likely just the rating of the most common wire insulation. If you have ever purchased wire for a home improvement project, you may have noticed its insulation is rated for 600 volt, even though household electricity will never see half that voltage. If anyone knows why 600 volt rated insulation seems to be so common in lower voltage applications, please leave a comment below and fill us in. Right before I finished putting this video together, I came across this Twitter thread where Jason Hughes elaborates further. He says, quote, the V3 stations can do 800 volt, although the cables for V2 and V1 cannot. There are some stations with V3 backend and V2 front end. At this point, V3 stations are about to surpass pre-V3 on number of connectors in the wild and climbing, end quote. The backend he is referring to is the cabinet that converts the incoming grid power into high voltage DC. You will typically see a few of these cabinets in a fenced-off area near the charging stalls. The front end would be the actual charging stall the user interacts with. So this would seem to indicate that all V3 superchargers are ready for 800 volt vehicles, and that while some V2s would just need the stalls upgraded, the majority of V2s would need the cabinets and stalls upgraded. In another tweet, he mentions that superchargers typically are field certified and that the specs can change from what is printed on the hardware. He later continues, quote, I don't think the issue with Tesla and 800 volt is much to do with the network lock-in, but long-term reliability and safety. With 800 volt, you halve the number of cells per group. In the event of a single cell issue, pop self-fuse, you now lose about 4% usable capacity versus under 2% with 400 volt, end quote. This is a really good point I hadn't sufficiently considered in the last video. The fewer the cells in parallel in each group, the bigger the impact if one fails. A fatal flaw in the battery pack I proposed are the strings of 138 cells in series. If any one cell failed, it would make the entire 138 cell string unusable to the pack. There is another possible way to arrange a 138S 6P pack though, that we'll look at a bit later. He then explained that Tesla is actually already building almost all of the current high voltage power equipment with 800 volt plus capable hardware. In typical Tesla fashion, this hardware has been changed and upgraded several times since the report I mentioned earlier was published. These changes were apparently done in the pursuit of higher efficiency rather than higher voltage. Utilizing the current hardware at 800 volt is another story though, requiring, quote, minor design changes all over the place. So let's summarize what we know so far. Tesla made clear in the Q1 earnings call that while 800 volts could be used for Semi and Cybertruck, it offers little benefit to the 3-in-Y platform and no benefit to the future robotaxi model. Other automakers are jumping on the 800 volt bandwagon for three main reasons. One, their suppliers have done the majority of the engineering legwork for them already. Two, the higher voltage is needed for high charge rates on CCS infrastructure. And three, it gives them a big flashy number to market. Tesla, on the other hand, has not needed to pursue higher voltages since they have focused for most of the past decade on extracting all the performance and efficiency possible out of their 400 volt architecture. While much of Tesla's current vehicle hardware components are capable of operating on 800 volt, many minor changes would be required to start utilizing it. On the charging side, V3 superchargers are allegedly capable of 800 volts, but V2 stations will need to be upgraded. Alright, given all this information, let's reevaluate what this means for the new Model Y out of Texas. In the last video, I suggested the 828 cell pack shown at the Cyber Rodeo event would be arranged as a 138S 6P pack with 6 strings in parallel of 138 cells in series. This type of arrangement would not be feasible when it comes to battery management and reliability. The failure of just 3 cells could turn half the pack into dead weight and likely render the car unusable. A smarter way to arrange the same 138S 6P pack is shown here. Thanks to Max for this diagram and the helpful discussion. This arrangement solves the battery management and reliability issues, but does pose a challenge of needing to bridge a parallel group between 2 modules. I'm not aware of any EV battery pack that has done this, but it also doesn't seem like an insurmountable hurdle. This 138S configuration seems like a winner given how well it adds up with the rumored 98 watt-hour per cell figure. Since 138 is the only common factor that would allow a common voltage between these 3 potential pack sizes, I don't doubt this is still Tesla's long-term solution. However, there is one other possibility worth discussing. In the last video, I mentioned that a 92S configuration was possible for the pack shown at Cyber Rodeo, but that reducing the number of cells in series would only make sense if the cells used a higher voltage. Well, that might actually be possible. At Battery Day, Elon said,
It's relatively straightforward to do a cathode that's 2/3 nickel, 1/3 manganese, which would then allow us to make 50% more cell volume with the same amount of nickel.
I hadn't really heard of this 2/3 nickel, 1/3 manganese cathode before, so I did a little searching. I first came across this paper from 2010. This study concluded that this cathode material can be charged and discharged repeatedly to 4.6 volt, which is higher than the typical 4.2 volts, and for many cycles even without surface coatings and without electrolyte additives, which I'm guessing is what Elon meant by straightforward. At 4.6 volts per cell, a 92S configuration would yield a 423 volt pack, which fits right between the current 3Y packs and the new Plaid S and X packs. This would also retain compatibility with V2 superchargers. An apparent downside to this 92S configuration would be that it can only produce this 828 cell pack using the 69 cell ribbons that were shown at Cyber Rodeo. Other pack sizes would need to use a different number of cells in series or a different number of cells on each ribbon. Therefore, if they are using a 92S configuration and can only build an 828 cell pack for the standard range model, either the rumored 98 watt-hours per cell would have to be wrong, or there would have to be a massive, roughly 13 kilowatt-hour software-locked buffer. In the recently released impact report, Tesla said they will continue to advance a diversified cathode strategy for LFP, nickel-rich, and manganese-rich chemistries. While Tesla had shown a nickel and manganese cathode for long-range vehicles at Battery Day, I believe this is the first confirmation of Tesla working on a manganese-rich cathode specifically. Tesla could be using this straightforward 2/3 nickel, 1/3 manganese cathode as a stepping stone to future manganese-rich and high nickel cathodes. Now that we've seen how the possible 92S and 138S configurations could work, let's step back and weigh the supporting evidence for each. First, a 138S configuration would result in a higher voltage than is used in the Plaid Model S. It is difficult for me to justify why the standard range Model Y would use a higher voltage than was needed for the quickest sedan in the world, so I'll count this as a point for 92S. Along the same lines, if Tesla is using this 2/3 nickel, 1/3 manganese cathode, and each cell can reach 4.6 volt, a 138S pack would then exceed 630 volts, rendering 600 volt insulation insufficient. A pack voltage this high would also be incompatible with V2 superchargers. If the reliability of initial 4680 cells is a concern to Tesla, the 92S configuration would likely be the preferred option due to having more cells in each parallel group. On the other hand, the 92S configuration would not be adaptable to other pack sizes and could only produce the 828 cell pack shown at Cyber Rodeo. If this is the case and the 828 cell pack is being used in the standard range, then there would have to be a huge software locked buffer, or the rumored watt-hour per cell figure would have to be false. Whereas the rumored 98 watt-hours per cell figure would line up perfectly with the required pack sizes for standard range and long range packs. 138 also happens to be a factor of 4,416, which means the existing long-range 2170 packs could be reconfigured to use the same voltage. This could also potentially simplify 2170 pack production, as I mentioned in the last video. The last benefit of the 138S configuration is the increased potential charge speeds using CCS. While the higher voltage of 138S would enable CCS charging at over 300 kilowatts, 92S would still enable up to around 220 kilowatts. Since a standard range Model Y is unlikely to be capable of charging faster than 220 kilowatts, I'm not sure if I would even count this as a strike against 92S. Given these facts, what do you think? Will Tesla really build a standard range Model Y with a higher voltage than the Plaid Model S? Will Tesla be using this new cathode with 2/3 nickel, 1/3 manganese, or something more traditional like NCA or NMC? Let me know what you think in the comments below. I'd like to give a big thanks to my supporters on Patreon that keep this channel going. I'll see you all in the next one.